Okay, Bluetooth. So what is Bluetooth? Bluetooth is a short distance being a few meters, control data and audio communications wireless technology. So the main purpose for audio in any case is to avoid wires between the devices, such as headphones and a media player, or a smartphone and a headset, a phone and a headset. Bluetooth uses low power frequency hopping radio in the 2.4 gigahertz band. Communication is two-way for handshaking, metadata, etc. Some profiles support duplex audio in both directions simultaneously, and some are only one direction per connection. So typical uses for Bluetooth are things like a mouse, a keyboard, cell phone, headphones, hands-free, talk and listen. And you can also have things like heart rate monitors. You can have a hands-free kit in your car. There are also devices that you can put in your running shoes that will communicate with your smartphone. So anything for passing data around. Now, there are two levels of audio quality. This is a little bit of a joke. The two levels are not so good and worse than that. So not so good is the stereo music profile, and the other is for voice communication. So the lower performance level is designed for voice-only phone communications, and it's notoriously poor. It's getting better, but it's not so good. Those of you that have Bluetooth devices probably know that. The higher performance level audio is designed for listening to music and audio from video presentations, and it's been described as near CD quality, being close to CD quality. Bluetooth has about 30 profiles that describe the capabilities and/or current operating modes for Bluetooth devices. So for devices to communicate, they must support and share a common profile. For example, a wireless mouse like this uses the HID, Human Interface Device Profile, which has no audio capabilities. Wireless headphones use the A2DP profile, which has no cursor control capabilities. So you can't connect your headphones to your mouse. Surprise, surprise. Oops, sorry. Now what's going on? So the APX Bluetooth option supports 3 Bluetooth audio profiles, and a 4th profile supports control functions related to audio players. So the audio profiles are A2DP, AVRCP, HFP, and HSP. And these will be described on the next few slides. So A2DP stands for Advanced Audio Distribution Profile. This is the profile that supports the higher performance audio, stereo audio that is near CD quality. Now the supported profile roles are, these are the roles that the APX analyzer plays in connecting to devices. So we can be the the source. In other words, the audio comes from the APX to a device, or we can be the sink. In this case, audio flows only in one direction, from the source to the sink. AVRCP is the Audio Video Remote Control Profile. So this profile is used in conjunction with A2DP, and it provides transport control. So for example, for headphones, you can click a switch and the media player will skip to the next track or go to the previous track or pause, that sort of thing. And that's using this AVRCP profile. Supported profile roles are the controller and the target. So the controller sends the commands, the target receives the commands. HFP stands for hands-free profile. This profile supports only the lower performance level audio. So the supported roles in APX are audio gateway. In other words, when we play the role of an audio gateway, we simulate a phone, like a smartphone. Audio flows in 2 directions at the same time, bidirectional, connecting the audio gateway device to the hands-free device. And these AT or telephone commands and other data are also supported, including commands like dial, redial, answer, hang up, caller ID, and so on. HSP is the headset profile. This profile is a simpler version of HFP, and it lacks some of the advanced phone functions. HSP is used by devices that use the voice band audio, but they don't want the complexity of phone functions. So some devices that connect to hearing aids, for example, use this HSP profile. It has the same roles and audio features as HFP, but it doesn't have the commands such as redial and hang up and that sort of thing. Here's a picture of the Bluetooth module in an APX audio analyzer. So the 555 shown here has a Bluetooth module. It consists of a hardware interface module and supporting software features that are available in the APX 500 software. The hardware module contains one Bluetooth radio. So it shows a source LED in red and a sync LED in green. And the radio signal is available on a female end connector. And we also, it comes with a smaller adapter to an SMB type, and the little antenna is an SMB type antenna. All APX audio measurements and sequence automation are unchanged for Bluetooth testing. So once you've paired with the device and connected to it, you can test it just as though you're connected with a wire. The only differences are additional choices and settings available in the signal path setup. There's an additional Bluetooth monitor view and some specialized sequencer steps. So in signal path setup, you choose on the input-output tab, for output you can choose your connector as Bluetooth. And for either the input or output, Bluetooth is just another connector that shows up in the menu of available connectors. But as soon as you choose it, the Bluetooth settings dialog opens up to prompt you to choose a set of profiles. So this is the Bluetooth settings dialog, and we'll go through this in a demonstration later. And the next choice is a set of profiles. So when you first open it, you haven't selected any profiles. So this slide shows the roles in A2DP. This is the music profile. So APX can play the role of a source. So it streams music. It simulates a media player and streams stereo audio to the sync device. And the sync device can send commands like play, pause, stop, next, etc. Now, in this role, APX can receive these AVRCP commands and keep a log of them, but it does not obey them. For example, if the device sends a stop command, APX will not stop sending the data. It will just keep a log of the fact that that command was sent. When APX is an A2DP sync, it can also be an AVRCP controller. So in this case, the device under test sends stereo audio to APX. APX can analyze the audio coming to from the device, and it can also send these AVRCP commands like play, pause, stop, next track, and so on. This slide shows the APX roles in the hands-free or headset profiles. So the audio gateway, in this role, APX simulates a phone. It can send and receive audio in two directions. And it can also send and receive commands to call, answer, hang up, etc. It can also assume the role of a hands-free device or a headset device. In this case, bidirectional audio can be sent to and from the phone, and it can also send and receive call and answer commands, etc. Now, before you can test a Bluetooth device, there are 3 steps that you need to go through, called discovery, pairing, and connection. Discovery means that you have to, the analyzer has to discover the test device. So most devices are not what we call discoverable by default. You have to put them in a special mode to make them discoverable. Once you've discovered the device, you have to pair with the device. Pairing establishes a mutual secure relationship between devices that have at least one compatible profile. Pairing is stored in a non-volatile memory in each device, and devices can pair with more than one other device. So there are different types of, different styles of pairing. The old style pairing is called legacy pairing, and the newer style is called secure simple pairing, or SSP. In the old style pairing, typically the user would enter a secret personal identification number, or PIN, a 4-digit number, usually into one device. In some cases it could be 2 devices, but quite often, you know, in the old days you would get a headset and it would say the PIN was 1234 or 9999 or something like that. With the new style SSP pairing, there are different ways of doing it. If devices have like a screen and a keyboard, you know, it might say type this number onto the keyboard, or you might get a prompt like do these 2 numbers match, or it can use a mode that's called just works. It says, do you want to pair? And if the device says okay, then they pair. Now the third step in this process is connection. So paired devices can connect using compatible profiles and roles. The connection enables exchange of audio or control data. Each device can connect with only one audio device at a time. And I think this information is a little bit dated. I think the newer devices are able to connect to multiple devices at a time. So this is just a flow chart showing the process for discovery, pairing, and connection. I don't think we'll spend a lot of time on this, not too important. So this is the Bluetooth discovery in APX 500. So the very first thing you need to do is select a set of profiles for your device. And this is a very important step. So if I have, if I want to connect to a smartphone from APX, I have to choose a role in APX that's going to be a hands-free device. Because if I try to be the audio gateway and I try to connect to an audio gateway, it's not going to work. So you have to be very careful to select the right profile set. So once you've selected a set of profiles, you need to make your device discoverable. So I'm not sure, I know for the iPhone, what you would do is go into the settings panel, open the Bluetooth menu, and as soon as the Bluetooth menu is open, the device is discoverable. So it's visible to other devices in the area. Then you can click on this button called Scan for Devices. You give it a scan time, the duration of time that you want to scan, and it will go through and find all of the devices that are within range. It'll first return their addresses, and then it will go back and find their what's called the friendly name. Once you've completed the scanning process, you click on the device that you want to pair to, and you can either right-click and select pair, or there's a little button that you can press that will pair. And depending on the pairing mode, it's either SSP, you might require a PIN, or it might just work automatically. Once you've paired, the device will show up as paired in the list here. Now the connection step, you can, once you're paired with the device, you can click on this connect button, and you can either connect all profiles, a single profile such as A2DP, AVICP, or HFP. And once you've selected the connect, it'll take a little bit of time for the 2 devices to negotiate a connection. This is used to select the A2DP settings that you want to use. Now in the APX software, the Bluetooth profile set choices are global and project-wide. So most devices can be fully tested with one of these profile sets. Typically a device is either an A2DP sync or a source. It's not both. There are certain devices, for example, we have some in our lab that are, they can be either a source device or a sync device. They have 2 Bluetooth radios in them. So in that case, you would need to use a different project file for each mode. You can't mix the two modes in the same project file. Some of the other details, the Bluetooth settings dialog allows other settings and actions. So there are some things in here that you can create a custom device class. This is the default device class for the APX analyzer. You can change its friendly name. By default, it has the, I think, the model number that you're using. Sorry. It has, this is the Bluetooth address of the module inside APX, and you can also change, you can't change that, but you can change this 4-digit PIN. And then you have some interface settings like which codec you want to use. So the two codecs that we support in APX are the SBC, of course, that's mandated by the Bluetooth SIG. And then aptX, which I think the gentleman was talking about this morning, that's an optional codec. You choose, you can choose a sample rate for A2DP, and basically this is the preferred sample rate. You don't always get the sample rate that you want. It depends on the strength of the wireless connection. If you have a poor connection, you may not get a sample rate that you've asked for. The devices also have to support the same sample rates. I believe, not sure if this is still true, but in the Bluetooth standard, it was mandatory that devices could stream 48 kilohertz in one direction, but they were only required to stream 44.1 in the other direction. So in one direction, 48 kilohertz was optional. And then you have some control over settings for SCO and eSCO. And the MSBC, that's for the newer wideband voice. We also have some Bluetooth monitors in APX. So this is in the same area of the software we'll look at, where you have some fields like the device name, the device address, the link key. So if you're using a device called the Bluetooth sniffer, that allows you to intercept packets in the air. And when to use such a device, to make a connection, you need this link key. So you link with your device, and then you can copy this link key with the mouse and paste it into your sniffer software. So you have some various parameters shown here in the monitor. There's also an actions button, which you can use to do things like connect or disconnect and send some Bluetooth commands. Similar to the other interfaces that we test, there's a status bar, and when Bluetooth is the input, it shows the input type as Bluetooth. It shows the name of the connected device, shows the profile here, A2DP, the codec in use, SBC, and the sample rate, 44.1 kilohertz. So SBC is a codec, an audio encoder and decoder based on subband coding. And as I mentioned, the Bluetooth Special Interest Group, or the Bluetooth SIG, has specified that the SBC codec is mandatory. Typical sample rates in A2DP are 44.1 kilohertz. Some devices use 48 kilohertz. And as I mentioned, a lower rate may be negotiated depending on the wireless signal strength. When the APX is using Bluetooth for the output, it shows, of course, Bluetooth, the name of the device, and the profile set. Here it's HFP. In this view, we see that the SCO, or SCO, is not connected. SCO stands for Synchronous Connection Oriented Link. It's a Bluetooth protocol used for voice data transmission. When the SCO is open, it will show the codec here. So the default codec for narrowband voice is the CVSD codec. It stands for continuously variable slope delta modulation. This is the most common codec used for Bluetooth profiles, HFP and HSP, used in telephone applications. And this has an 8 kilohertz sample rate. So MSBC is a new codec, stands for Modified SBC. This was added recently in HFP 1.6, the hands-free profile 1.6, for wideband voice. It uses a sample rate of 16 kilohertz, so higher quality. So these are some of the actions when APX is the audio gateway. So you have a start streaming button, and then you can force open the SCO. You can dial a phone call, or you can ring a phone. You also have a button for sending AT commands. When APX is the A2DP sync, you can send these AVRCP commands. So if you click this button, a little panel opens up, and it allows you to send commands like previous track, next track, fast forward, fast reverse, change the volume, and mute, etc. And then in terms of AT commands, you have a button to redial the last number or hang up, or you can send an AT command. So just included a little case study here. We've often gone to these events called Unplug Fest. So this happens, it's organized by the Bluetooth SIG, and 3 times per year people come from all over the world to test their devices with other Bluetooth manufacturers. And at one of these events, I met with an engineer who had a Bluetooth car kit for communicating in the car. And a lot of times when you go to these events, you know, the guys will be standing there, they connect their devices, and they have a little microphone, and they go, hello, 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 can you hear me now? Can you hear me now? And he said, when I'm connected to other Bluetooth devices in the hands-free profile, the audio I receive from them sounds good. But the audio received when I speak into the microphone sounds bad. So I said, well, let's do some tests and see what we can work out. So first thing we did is connect the APX analog generator to his device and analyze the speech signal received over Bluetooth. So we discovered his device, paired with it, and then connected. And we're going to talk about PESQ in a little while. This is one of these perceptual audio measurements. So you generate a sentence, a speech sentence, through the device. The APX measures what comes out, compares it to the original, and it gives you a score between 1 and 5. So 1 is very poor, 3 is sort of average, 5 is excellent, but he got a score of 1.22, which is not very good. And it was using wideband voice, so the score should have been closer to 4.0, maybe 4.5 at the best. So I think if we're still hooked up, we can play this little sound clip. Let's see if this is still connected.
Half of the curtain slides back. They are men who walk the middle of the road. Both brothers wear the same size.
So that's a speech signal that's recorded at 8 kilohertz sample rate, sort of standard telephone quality. And this is what it sounded like coming from his device.
Yell and clap as the curtain slides back. They are men who walk the middle of the road. Both brothers wear the same size.
So it sounds okay, but it's pretty heavily distorted, right? So what we did next is we generated some pure sine signals through the device under test and observed the results. And in the following spectrum plots, you can clearly see something wrong. So here we generated a signal at 500 hertz, and this is sort of typical of a spectrum from this type of device. But look at this over here. There's a peak at about 8 kilohertz, or 7,500 hertz. That's only about 10 or 15 dB below the fundamental. When we change the sine frequency to 1 kilohertz, we got another frequency over here, slightly lower and at a different value, and so on. So you can see something going wrong here. So what's happening is the device under test has significant distortion due to a spurious tone that's related to the sample rate minus the frequency of the signal that we're generating. And the level of the tone increases as the frequency of the signal increases as well. So it's clearly a DSP problem. So next we looked in the opposite direction. We took Bluetooth in and analog out, the signal from the phone calling the car kit. And his observation was, in this direction the audio sounds good. So we connected the Bluetooth generator to his DUT again and analyzed the speech signal. In this case, we received a mean opinion score of about 3.4. Now, it was a wideband voice codec, so we would have expected a higher grade, like something like 4.0. So these are the speech signals again, this time in the other direction. Whoops.
Yell and clap as the curtain slides back. They are men who walk the middle of the road. Both brothers wear the same size.
So that's the original signal, and this is the signal coming through his device.
Yell and clap as the curtain slides back. They are men who walk the middle of the road. Both brothers wear the same size.
So do you hear the difference? If you listen carefully, you can hear much more high-frequency content in the original signal than in what was coming from his device. And if we then connected up to the analyzer and did some standard tests, and we found out, this is I think a step frequency sweep measurement, so we swept from 20 hertz up to 8 kilohertz, which is the bandwidth. And as you can see, the device was being filtered at about 3.5 kilohertz, which corresponds to the narrowband voice. So, so really he was using wideband voice, but he was filtering out the signal in the baseband of a narrowband signal, not a wideband signal. So again, it was another DSP problem. So that's just an example of approximately 1 to 1.5 hours. We were able to identify a couple of signals, and it's much more powerful than just speaking into the microphone and saying, hello, hello, can you hear me? Okay, so we'll do some demonstrations here, I think. So let me start back here from scratch. And I'm going to open my Bluetooth settings window and clear all devices. And we'll start, actually we'll just open a new project. So the device that I have here is it's like a hands-free device, and it's a little bit like a Bluetooth headset. So it supports both voice and stereo streaming. And the way this one works is you plug a little jack in here and you put a set of earphones on your ears. It's a nice device for demonstrating with APX because it has an analog output. We can plug a signal from the analog output into the analog inputs of the analyzer, and then we can send Bluetooth audio. So most of these devices, let me start from scratch. I have to turn it off. So normally they have a little LED on it, and if you hold down, there's a certain process that you have to follow to make it discoverable. So on this device, if I hold down this button, it starts to flash, and if I keep holding down the button, eventually it starts to flash a blue LED very quickly. And that means the device is discoverable. So once it's discoverable, I'll choose my output connector as Bluetooth. And in this case, this device is a hands-free device. So to test it, I have to play the role of a phone. So I want to be an A2DP source and HFP audio gateway. Now once I've done that, I'm now ready to scan for devices. So I've entered a scan duration here of 2 seconds. If you, just for speed, given the proximity and how close I am to the radio, it should be able to find it very quickly. So it's going to go out and scan. Found a few devices. You can see it found my laptop. It found somebody else's device, and the device I'm looking for is this one here. So it finds the Bluetooth address, which is a unique address for every Bluetooth device. And it also finds, if it can, the friendly name it's called. So this is a Jabra tag v2.00. So initially, I found the device, and I want to pair with it. So I can either click the pair button when it's selected, or I can right-click here and select pair. So this device, I think, uses secure simple pairing with a sub-mode that's called just works. So if something asks to pair with it, it will just work. But if it required a pin, I could add a pin in here. So I'll click pair device. It's in the process of pairing. And once it's finished, you can see that it shows up as paired here in this view. Now once I've paired, I need to connect. And I have a choice of A2DP, AVRCP, and HFP. And I'm going to choose all profiles. So now I'm connected. And you can see down in the status bar, you may not be able to read it, but it says output Bluetooth, Jabra tag v2.00, A2DP, SBC, and the sample rate is 44.1K. So if I turn on the generator, I should get a signal if I plug it in. Now I'm getting a signal on channel 1, but not channel 2, and it may be the volume control. Let me try this. Okay. I'm not sure if this is my cable or some other problem. Might just be this device has a bad connection in it. Okay. Well, for some reason, I'm just getting one channel of audio on this device. Not sure why. Perhaps it's broken, but we'll just carry on. So now that I'm connected, I can control my generator level in dBFS, and I can measure the analog inputs. So we can go ahead and do some measurements. One of the questions that came up was signal-to-noise ratio. What's a typical signal-to-noise ratio? So I can try this. Sometimes these devices don't like to be stimulated at full scale. Let's have a look. Let me go back here. And let's have a look at the spectrum as we turn up the generator. So that's minus 6 dB full scale. Minus 4, minus 3, minus 2, and 0. So at 0, second, okay. At 0, the output is 380 millivolts, and the distortion is 63 dB. So there may be something wrong with this device. Perhaps the battery is not charged. In any case, that's about typical. Well, you should get, if I was able to get a higher level, I would probably get a better distortion, but typically no better than about minus 70 dB THD plus N. For example, we could just go ahead and do standard audio measurements. So level and gain. Let's set the generator to 0 here. So we're measuring the level and the gain in dB relative to full scale. I think maybe what I'll do, since we're not getting a signal on channel 2, I'll just turn it off and look at one channel. Then we can look at THD plus N with the sine signal. I'll set that up at 0 dB. And we've got about, oh, there we have about 70 dB now in terms of THD plus N. Okay. So that's about normal for devices using the SBC codec that I've worked with. And if we look at signal to noise ratio, let me crank this up to 0. And we're measuring 20 hertz to 20 kilohertz. So it'll turn on the signal, measure the noise, and measure the difference. So we're getting signal to noise ratio of about 65 dB. Crosstalk we can't measure because we only have one channel active here. Now in terms of frequency response, something that you have to be careful with, and I'll show you, I'm going to add a measurement called continuous sweep. And here let's just try a chirp measurement. So let's go at maybe minus 6 dB relative to full scale. Look at the incoming voltage in dBV, and we'll just sweep 20 hertz to 20 kilohertz. And you'll notice that, I get a pretty nice looking response curve, but all of a sudden it falls off at a frequency of 2K. Now in our technical support department, we get this question very often, and it's pretty easy to figure what's going out, but you have to know where to look. So if you go back and look at the acquired waveform, which is the last result out here. Sorry, that's the wrong one. I want to look at, yeah, there's a result called acquired waveform. You can see that the signal is getting chopped off here. And as a result, we're getting an incorrect spectrum. So what's happening is there's a delay in the device because it has a codec, and it takes time for it to process all of the data signals. So if we look at the impulse response, you can see here, let me turn on the cursors, and you can see the impulse is peaking here at about, let's see, what is that, about 110 milliseconds? So I'll turn the cursors off. So there are two things I can do. I can add additional time at the end of the sweep with this extend acquisition by. But the other thing I can do is I can go into signal path setup, and there's a special field called device delay in here somewhere. Here it is, device under test delay. So I'm just going to enter in here, say 100 milliseconds, because that's easy to remember and it's enough to overcome this problem. And now if I go back and repeat this measurement, not quite enough. Okay, my impulse response So I need about another 50 milliseconds. So let me go back and make this 150 milliseconds. I think I must have measured incorrectly before. 150 milliseconds, okay. So we'll go ahead and measure a chirp. Now you can see the impulse is pretty close to 0, and the acquired waveform fits completely within the time block. And now if I go back and look at the RMS level, you can see a nice curve here. So that's my frequency response. The relative level, and this is the deviation from flatness throughout the band. So once you overcome the issues like delay, it's really just like measuring any other audio signal. Let's see. So some other things we can do here. In the Bluetooth monitors, we have, you can see a little Bluetooth logo here. And here you can see the device name, the device address, the MAC address. This is the link key. And if I right-click here, I can select things like copy Bluetooth address or copy link key, and I can open the Bluetooth settings window. So it shows the status of the HFP control is connected. The SCO, which is used for the telephone communications, is closed. The A2DP is connected. Streaming is started. The codec is SBC. The sample rate is 44.1K. The channel mode is joint stereo. There are different variations you can do. Joint stereo, I think it puts the same signal on both channels. I'd have to check that. This is a bit pool. I think it indicates the strength of the connection, and AVRCP is connected. So if the other thing that we have here is an AVRCP log. So I believe that I could send commands to the device. There's a fast forward here, so you can see there I actually pressed it twice. Well, I pressed it and released it, so it gives you the date and time and when it occurred. Then I will do a backward press and release. I guess if I hold it, I've got to press, and when I let go, I've got to release. And then, let's see, there's some volume control commands here. I think we ignore the volume control commands because we're an audio generator and we don't want the device messing with that. Not sure if these other buttons do anything. Yeah, so I pressed the pause button there and released it, and pressed the play button and released it. So the pause and the play button are the same button. It just determines whether it's been pressed or not. So that's kind of a nice feature. You can keep track of Bluetooth commands. And then when you want to test, so right now we're looking at the A2DP profile. And if we generate a signal, we can see what it looks like. If I switch over to the voice profile, what I can do is from signal path setup, let's see, oh, it's up here on the panel. I have a choice of actions, so I can stop streaming, which leaves me connected. It just stops the signal, so there's no, the frequency sample rate is showing up as 0 hertz here. I can dial, so I can specify a dial command, and what that's done is opened the SCO. So if we look down here in the status bar, it's showing that I'm now connected in the HFP profile with the CVSD codec. So I'm still sampling on the input side at my baseband, but I'm probably going to get different response. So you can see here, this is the CVSD codec, and it really doesn't like to be stimulated at full scale. I have a component here that's about 50 millivolts and a very strong second order component. And probably if I reduce this level, that higher order harmonic will go away. But so we talked about the A2DP codec having a maximum THD plus N ratio of about 70. The codec is terrible. The best it can do is about 20 dB. It's really pretty bad. Let's see, some other things we can do here. Any of the measurements, if you right-click and select Edit Prompts and Properties, there are some steps that we can do in Bluetooth. So we can enable wideband speech. We can do some A2DP commands like start streaming and stop streaming. Or for the audio gateway, we can open the SCO, dial, ring, close the SCO, hang up, or send an AT command. There's some other steps at the beginning of the sequencer, I think on the signal path setup. There are some special Bluetooth steps here, I believe. Bluetooth, yeah, so you can connect device profiles, and you can choose all profiles or one of the specific profiles. Let's see, what else have we got in Bluetooth? You can disconnect the device, and then just like any of the other measurements, you can enable wideband speech, the A2DP source, and HFP audio gateway. And I believe there are some commands up here as well under project sequence properties. At the start of the sequence, maybe not. Oh yeah, there's some parameters. You have a delay for opening and closing the SCO during the sequence. Okay, so these are perceptual audio standards for voice quality. They were jointly developed by the ITU and Opticom from Germany. And there are two standards in effect. ITU P862.2, PESQ. That's an acronym for Perceptual Evaluation of Speech Quality. And P863 for POLQA, which stands for Perceptual Objective Listening Quality Analysis. Quite a mouthful. So here's a resource that you can download from ap.com. We have a tech note number 121 on perceptual audio testing. So the concept that both of these measurements use is called the mean opinion score. So how this was developed originally, they had panels of listeners. They might get 30 people at a time, or not always at the same time, but they would play them a series of sentences that had been recorded with different impairments. And the people would listen to the sentences, the reference sentence and the impaired sentence, and they would give it a score between 1 and 5. So 1 being very low quality, 5 being the best quality. And statistically, people would analyze the scores from all these different listeners, and they would come up with what's called a mean opinion score. They would take the mean of all the listeners and give it a score. So that was the origin of the measurements. Those were subjective listening tests. And as you can imagine, it's very expensive to do those tests. You have to get lots of people to come into your facility and train them, and they have to spend many hours listening and grading it, and then you have to analyze the results. So the whole impetus was to come up with an objective listening test that could be done by a machine algorithm very quickly and very inexpensively. So the way these measurements work is you have a reference signal. It's typically a recorded sentence that's spoken. It's generated through the device under test, and this objective measurement method compares the signal from the device under test to the reference signal and gives you an estimate of the speech quality, or a mean opinion score. So the MOS scores vary from 5 for excellent with imperceptible impairment. That means you can't tell there's any impairment at all the way down to 1, which is bad, and it's very annoying to listen to. You know, if you talk to somebody on the phone, and you've probably been connected on very bad cell phone calls, and you can't hear what the person's saying, it's terrible. So that's the mean opinion score. So we have 2 PESQ measurements in APX, and these are software options. They require a license key that's installed on a little button. So there's a connector that plugs in the back of the instrument, and a little license key button goes into that connector. Now the reason that it's licensed is that we have to pay money to this company Opticom to license the technology, and they charge us for every license that we sell to a customer. So we have to pass that charge on to the customer. So PESQ is one of the measurements that we have, and this just does a single comparison of an acquisition, a series of sentences, to a reference waveform. And then we have another measurement called PESQ averaged, and what this does is you can compare multiple acquisitions to 1 or more reference files and produce an average score. So they both work in a very similar fashion. We can demonstrate them here in a minute. So here's the PESQ block diagram, and if you want, you can download a white paper from the Opticom website, and they talk about everything that goes on here. There's a lot of signal processing. So the reference signal comes in, it's level aligned, there's an input filter, the signal passes through the system under test, the degraded signal has a level alignment and an input filter. The 2 waveforms are time aligned, and then it goes through a series of processing and comes out with a prediction of the perceived speech quality, in other words, an MOS score, mean opinion score. So the PESQ algorithms work with any waveforms which are sampled at 8 kilohertz or 16 kilohertz. And there's a maximum length of 35 seconds for the file being analyzed. They're designed to work on complex signals like speech, and we provide many waveforms with the APX 500 software. So I'll be demonstrating that during the demo. This example shows the instantaneous level versus time of the reference waveform on the left and the acquired waveform on the right. And there's a little checkbox here in the display called Show Dropouts, and that will show dropouts in the signal. In other words, when the signal was disconnected. So these are the PESQ results. The MOS score is the normally reported value. There's another score called PESQ, which is related, but it's only valid for narrowband analysis. And the acquisition time can be extended for devices with delay between the input and the output. So we have MOS, P862.1, PESQ, MOS versus time, the average delay, the delay versus time, the acquired waveform, and the reference waveform. MOS versus time, shown in this graph, is for debugging only. It's not really sanctioned by the ITU. The PESQ average result, the way this works is you select a series of files, and it will generate those files in sequence. So you can either add the same file multiple times if you want to test it 3 or 4 times in a row or more, or you can add a series of different files with different sentences. And you can change the order of these sentences using this control. So this has 2 results. There's an MOS average score that's averaged over all of the test signals, and then an individual score for each signal. this shows the MOS average score, and this graph shows the individual scores that are accumulated into the average. This is a derived result that we have in the APX software, so you can right-click on any of the results and select Add Derived Result, Data Distribution, and this will give you the standard deviation or the 95% confidence interval. So if it works on these measurements that have multiple results, like the MOS individual results. And you'll get a result like this showing the mean value plus the confidence interval. Oh, we've already talked about this case study. Not sure why it's in here twice. Let me just skip ahead. So this is POLQA. So POLQA measurements in APX is very similar to PESQ. So POLQA is really it's an evolution of the PESQ measurement. It will gradually replace PESQ in the future, but currently there's a large volume of work, particularly from telephone companies that have used PESQ in the past. And the thinking is that they will gradually switch over to POLQA with time because it's a more powerful and a newer algorithm. So POLQA works just the same way. There are two measurements, POLQA, which gives you a single acquisition to a reference waveform, and then a POLQA averaged measurement, which compares multiple acquisitions, just like the PESQ average, actually. Here's the POLQA block diagram. I'm not going to go through this in any sort of detail. If you really want to dig into it at this level, I would suggest getting, there's some white papers available from the Opticom website that you can download. And these are the POLQA results. So it has a mean opinion score. That's the one that's normally reported. Again, the acquisition time can be extended for the devices with delay. And then we have, in addition to MOS, the POLQA G107, MOS versus time, average delay, delay versus time, acquired waveform, and reference waveform. This, similar to PESQ, shows the POLQA reference signal on the left and the acquired waveform on the right. So here, there's a little checkbox called Show VAD Regions, and that's showing the regions of active speech in the signal. The algorithm ignores these blank intervals of pauses between sentences or little components of speech. This shows the MOS score and the MOS versus time on the right. And then this is an example of the POLQA averaged measurement. So we have a series of waveforms here, and you can see the individual scores shown in this graph on the right. And then we have the POLQA averaged score. So that's it. We'll just do a quick little demonstration, and then we'll get you folks out of here. So let's go connect to the software here. So I think what I'll do here is I will just switch to analog, unbalanced, and use a loopback connection. Let me just check the generator. And I'll use one channel. Okay, so let's add some perceptual audio measurements. So I'll click the Add Measurement button, and there's a special tab here called Perceptual, and I will just select all of these by doing a click and a shift click. So if we look at PESQ here, now there's a default waveform here. So there are two, one at 8 kilohertz and one at 16 kilohertz. We can just start with those. The So you have a mode control here. You can choose narrowband or wideband. And then there's this extend acquisition time value if you have delay through the device under test. You can also check this save to file box, and in this case the system will save a WAV file of the acquisition that you can listen to or work with later. So let's just go ahead with the default, and what I'll do here, let me try, I'll try a higher value. Okay, so what the system is telling me here, it changed ranges during the measurement. So you want to avoid range changes because the analyzer can't handle it. And this is a consequence of the fact that these speech files have a very high crest factor. You know, a sine wave has a crest factor of about 3 dB. Speech is typically in the order of 12 dB or higher. So we can try, in advanced settings here, I'll just change the input range to something like 1 volt. Let's see if that works. So it's acquiring the signal. Yeah, so in loopback mode, I get a score of 4.55. So if we try turning on the audible monitor here.
Yell and clap as the curtain slides back. They are men who walk the middle of the road. Both brothers wear the same size.
Just to give you an idea of what the sentence sounds like. And then let's go ahead and try the, oh, so one thing to note, if we, so that's there's one waveform included in the APX software that's called the default. If you click the browse for file, just get a warning dialog here, but if you choose yes, it automatically goes to a folder that's installed with the APX software, and there are a variety of waveforms. So these are recorded by people at Audio Precision. There are, let's see, 2 females with 4 different sets of sentences, and 2 males with another 4 sets of sentences, and they're 2 different sample rates, 8 kilohertz and 16 kilohertz. So you would use the 8K for narrowband speech and the 16K for what they call wideband speech. For PESQ, you can actually make your own sentences. So for example, if you wanted to test in Korean language, you could just record your own sentences. What we used, there's a set of sentences that have words in them that are balanced and meant for this type of work. In the US, they're called the Harvard sentences, I believe, and you could probably find similar sentences in Korean, and you just have someone read them and record them professionally, and then you can use your own. They're typically about 10 seconds long. So let's go ahead and do a PESQ averaged measurement. And actually, before I do that, I think what I'm going to do is go back here and in the audible monitor, instead of automatic, I'm going to try something a little more reasonable. So let's try, hopefully that won't be too loud.
Yell and clap as the curtain slides back.
Okay, that's good. So we'll go to PESQ averaged, and here I would choose the generator level. I'll choose the same one I did here. I'm also going to fix the input range to avoid that overranging issue. And then I will choose a series of files. Well, that's interesting. I would have expected this to go to the same folder. Well, I can use this opportunity to show you where to find it. So we'll look in Program Files x86, Audio Precision, APX 500 4.1, Waveforms, PESQ. And let's just grab a series of, we'll do, I don't know, female. I'm just going to click a few here. Okay, so I think I've just picked female 1, female 2, male 1, and male 2. So that's 4 files. And yeah, we can just go ahead and flip over to the time domain view here.
Try to have the court decide the case. They are pushed back each time they attack. He broke his ties with groups of former friends.
So this is showing the average
Open
score.
The safe, but don't break the glass. Add the sum to the product of these 3. Thieves who rob friends deserve jail.
We talked at the slideshow in the circus. He ran halfway to the hardware store. Cars and buses stalled in snowdrifts. The frosty air passed through the coat. The crooked maze failed to fool the mouse. Adding fast leads to wrong sums.
Yeah, so when it completes, you can see the individual scores here, 4.63, 4.55, 4.64, 4.62, and then the average score of the 4 sentences. So you can queue up as many sentences as you like. So POLQA is very similar. Just a couple of things I want to talk about that are a little bit different here. So it works pretty much the same. Yeah. One thing about POLQA is it's very sensitive to the level alignment of the 2 signals. So the PESQ algorithm has what's called an auto level alignment. So it takes the reference signal. If the required signal is low, it will bump it up and match it. In POLQA, that's not the case. So you get penalized if the signal is too low or if the signal is too high. So we do offer this auto level alignment button. The other thing that's critical about POLQA is the waveforms are very special. In the case of POLQA, it would be hard for the average user to record their own waveforms. They have to be recorded at a very specific signal. They use a metric called the active speech level. So you ignore the pauses between sentences, and you calculate the average level, and it's supposed to be at 26 decibels below what's called overload, 26 dBOV. So for a digital system, that corresponds to minus 26 dBFS. For an analog system, you have to find the overload point, the point where your system starts to clip, and you have to adjust the level accordingly. So let's just go ahead and I can load one of these waveforms in here. I'll set the level just like I did before. And let's see, I need to change the range again so that it doesn't overload. I'll set this to 1 volt. Or 1.25 is the nearest range. And without checking auto level alignment, let's just see what score we get here.
We talked at the slideshow in the circus. He ran halfway to the hardware store. Cars and buses stalled in snowdrifts.
So you see I got a very low score. Probably what will happen, I mean I could figure out the right level that it should be recorded at, or I could cheat a little bit. There's also a warning indicator here. It says the level of the reference signal was higher than allowed by P863. That's a little bit unusual. And then the level of the degraded signal was higher than that allowed by P863. So let me try the auto level alignment here.
We talked at the slideshow in the circus. He ran halfway to the hardware store. Cars and buses stalled in snowdrifts.
So here I'm getting 4.50, which for narrowband speech is a perfect score in POLQA. So just something to be cautious of, especially if you're using an analog circuit. You know, you have to be careful about matching the level correctly. You have to find the overload point for your device. With POLQA, if you're testing acoustic devices, you know, you might be using a mouth simulator with a microphone, and there's a very specific level. I think it's 73 dB A-weighted, dB SPL, or 79 dB SPL A-weighted, depending on narrowband or wideband speech. So I think that's a pretty good overview. We could do the POLQA average, but you know, it's pretty much the same as the PESQ average. You just get a series of different scores, and it calculates the average. Yes. Yeah, there's a similar standard, and the acronym is what is it called? Perceptual. So Opticom has another measurement. I can't remember the acronym, but it's something like that. It's perceptual audio quality. PEAQ, that's right, PEAQ, perceptual evaluation of audio quality. And it's meant for things like compressed audio, you know, MP3 codecs and that kind of thing. And that is meant for, you know, stereo music listening. There's an interesting article on, I don't know if you've been to, McGill University has a DSP website. Perhaps you've been there, Dr. Lee. But they have a DSP lab, and they have, it's kind of a shareware version of a software that's similar to this perceptual audio for music that you can download and play with. I don't know if it meets the standard, but it's free, so you can try it out. Okay.